The first talk is concurrently composable, non-interactive secure computation, and Andrew Morgan will give the talk.
Thank you for the introduction. So yes, this talk is based on work done jointly with my advisor, Rafael Paz. We both regret that we're unable to make it to the conference in person, but we're happy to have the opportunity to present our work remotely. So to get right into it, in the setting of two-party computation, which we consider in this work, we have a receiver and a sender, both with private inputs, who wish to jointly compute some functionality F on their respective inputs, in such a way that a potentially malicious party participating in the protocol wouldn't learn anything about the other party's input besides what they could logically infer from the output of the protocol anyway. So formally, we call this notion simulation-based security, where a computationally bounded adversary should be unable to distinguish between their view of the real execution of the protocol and their view of an idealized execution with a trusted third party and simulated messages which are independent of the honest party's input. We note that secure computation was originally studied in an honest but curious or semi-honest setting where the adversary had to follow the protocol but could attempt to learn additional information. But in this work, we consider fully malicious adversaries which can deviate arbitrarily from the protocol. If we consider one-sided functionality, where only a single party needs to receive the output, a minimum of 2 single message rounds of communication is necessary to avoid residual attacks. Protocols achieving this minimum are referred to as non-interactive secure computation, or NISC. NISC protocols with trusted setup are well known. In the plain model, it is just as well known that 4 single message rounds are both necessary and sufficient for maliciously secure two-party computation under standard simulation-based security. So, to construct NISC in the plain model, it is necessary to use a standard relaxation of security known as super polynomial time simulation, or SPS, where the simulator is allowed to run in slightly super polynomial time. If we relax our security definition to SPS, it turns out that NISC with malicious SPS security in the plain model is possible and can be constructed based on sub-exponential versions of standard assumptions such as decisional Diffie-Hellman, residuosity, or learning with errors. However, for a lot of potential applications of secure computation, we need stronger security properties than are guaranteed by standard simulation-based security. In practice, protocols can be run concurrently with many simultaneously active instances and an adversary able to adaptively observe the results of certain interactions and use them to influence others. And also, protocols can be run as a sub-protocol in a larger composition of protocols, where we would intuitively wish to guarantee that a composition of provably secure protocols is likewise secure. Neither of these two properties are implied by the most basic definitions of simulation-based security, which we henceforth refer to as standalone security. Some of the classical definitions of simulation-based security did consider a composability property, but the first framework to guarantee both concurrent and composable security is the well-known Universal Composability Framework, or UC, proposed by Canetti in 2001. To prove that a protocol is UC secure, one needs to show an analog of simulation-based security, but against a much stronger external party than a classical adversary, an environment which can invoke many concurrent instances of a protocol, corrupt potentially many parties, and observe and control corrupted parties' communication. As such, it's a strictly stronger notion and thus more difficult to prove than classical simulation-based security, but correspondingly provides stronger security guarantees. Of course, because it is strictly stronger, UC secure two-party computation with polynomial time simulation is subject to the same impossibilities in the plain model as standalone security. So to even consider building UC secure NISC, we need an analog of SPS security. Simply allowing super polynomial time simulation in the standard definition of UC security doesn't preserve composability. So instead, in this work, we consider a notion of angel-based or oracle-aided UC security, where the environment and simulator both have access to a specific super polynomial time helper oracle, or angel H, but are otherwise restricted to polynomial time. The added strength of UC security in comparison to standalone security also means that historically we have a far more limited space of results for UC secure two-party computation than we have for standalone security. As I mentioned earlier, standalone SPS secure NISC is already a solved problem. But even considering concurrent security without composability, the most efficient two-party computation protocols prior to our work are protocols where all parties receive the output and thus require 2 rounds of simultaneous broadcast where every party sends a message simultaneously. And thus these protocols would require 3 single message rounds for two-party computation in the single message setting we consider. Furthermore, if we want both concurrently and composably secure protocols, the best known constructions prior to our work require an unspecified constant number of rounds of communication. So it's remained an open question whether concurrently and composably secure NISC, or for that matter, even concurrently secure NISC for general functionalities, can be constructed with malicious SPS security in the plane model. So our work answers that question in the positive by providing a construction of NISC that does achieve angel-based UC security and shows that the minimum of 2 single message rounds for two-party computation can be achieved for this considerably strengthened definition of security. Specifically, our construction of UC secure NISC, which we dedicate the majority of our paper to presenting and proving formally, requires 2 key building blocks: a standalone sub-exponentially SPS secure NISC and sub-exponentially secure non-interactive CCA secure commitments. Concerning the realizability of the assumptions, the standalone SPS secure NISC is, as I've mentioned, well known from sub-exponential versions of standard assumptions. Non-interactive CCA secure commitments, on the other hand, are considerably more involved, and I'll turn to a brief discussion of those now. So these are tag-based commitments, which are non-interactive in that committing to a value requires a single commitment algorithm rather than an interactive process. And they satisfy a binding property that a commitment can't be open to 2 distinct values. And most notably, a strengthened notion of chosen ciphertext hiding, analogous to the notion of chosen ciphertext security for encryption, which is defined by a security game where an adversary is allowed adaptive query access to a decommitment oracle, which we call O*, which on receiving a commitment returns the corresponding value in randomness usable to produce that commitment. So the adversary will then interact with a challenger C, giving it an adaptively chosen tag and 2 values to commit to, and the challenger C will respond with a commitment to a random one of the 2 values. So the adversary then breaks security if it can correctly guess which value the challenger committed with probability significantly greater than 1/2, and without having queried the decommitment oracle in any commitment that has the same tag as the challenge. In this work, we also consider a relaxation of CCA security, which we call weak CCA security, where the oracle in response to a query returns only the value committed rather than both the value and the randomness. As it turns out, this relaxation is sufficient for our NISC construction. Unfortunately, the known constructions of non-interactive CCA secure commitments thus far do require more sophisticated assumptions compared to our other building blocks, standalone secure NISC. Their original construction relied on adaptive one-way permutations, a strong non-falsifiable assumption, and more recent constructions have been proven based on sub-exponential security of a variety of sets of assumptions, such as hinting pseudo-random generators, keyless collision-resistant hash functions, and time-lock puzzles, though the authors of this work remark that the former of these, hinting PRGs, can be based on standard assumptions such as sub-exponential CDH and learning with errors. Given this, it might be a natural question to ask whether we can potentially bypass the requirement for non-interactive CCA secure commitments and base concurrently composable SPS secure NISC on a weaker set of assumptions closer to the standard assumptions required for the base standalone NISC protocol in our construction. However, in a second key theorem in our work, we answer that question in the negative. We show that the implication from our first construction is basically bidirectional, and that non-interactive weakly CCA secure commitments are both sufficient and necessary to construct UC secure NISC. Specifically, alongside our initial theorem constructing the NISC protocol, we have a second theorem showing that given a UC secure NISC protocol such as the one we construct, we can build a non-interactive weakly CCA secure commitment scheme. This, combined with the fact that, of course, our oracle-aided UC secure NISC is a strictly stronger definition, trivially implies standalone SPS secure NISC, will imply that our construction in the first theorem is based on nearly minimal assumptions. There's a minor gap, which is that our NISC construction requires sub-exponentially secure primitives, while the primitives implied by UC secure NISC only have polynomial time security. For the sake of time, I'll defer the details of our second theorem to our paper, and I'll spend the rest of this presentation providing some insight into some of our ideas behind theorem 1 and our construction of NISC. So we begin by leveraging the properties of the underlying NISC to perform the computation of the joint functionality F, as might be expected. Of course, we need to guarantee UC security, which is not provided by the underlying NISC. And in technical terms, this will require the simulator we construct for a definition of simulation-based security to be able to extract a corrupt party's input from the message they send in order to deliver it to the ideal functionality in our idealized interaction. And of course, because the simulator we construct for Oracle-aided UC security is by definition restricted to polynomial time, as might be expected, we can't just leverage the super polynomial time simulator from the underlying NISC to do our work for us since it's super polynomial time. So instead, we rely on the super polynomial time helper functionality H, which we're given by our definition of Oracle-aided UC security. In our case, this helper will implement the CCA decommitment oracle O star, and it will extract inputs from commitments to messages that will be sent alongside the internal NISC. The tag-based security of the CCA secure commitment scheme we require will effectively guarantee that we can implement this helper functionality to only decommit commitments with corrupted parties tags. And this will ensure the adversary and environment, which are also given access to this helper functionality, can't just trivially break security by decommitting honest parties commitments. So, starting with the underlying NISC, I'll build up our protocol on the right side of the slides while discussing at a high level the steps we take to implement UC security as we add them to the protocol. So I'll start by considering the malicious receiver case. As I just discussed, we add the extractability necessary to provide simulation-based security by having the receiver commit to their input X and send it to the sender in the first round along with their internal NISC message. Of course, with that, we need to guarantee that the malicious receiver commits to the same X they input to the underlying NISC. And so we add functionality to the NISC to implement what can be thought of as interactive witness encryption. So the receiver provides the randomness that they use to commit to X. The sender provides the commitment they received from the receiver, and the NISC verifies that the commitment is valid and rejects it not. So this ensures that a malicious receiver can't receive the output from the functionality unless they sent a valid commitment to the sender in the first round. While we now have extractability for the receiver's input, there's another issue, which is that the simulator in this case needs to be able to simulate the sender's message in the interaction to send it back to the corrupted receiver. And what's more, looking ahead to the corrupted sender case, we'll also need a way to verify the correctness of the sender's input. And to do that without requiring an additional round, we'll require a super polynomial time simulatable zero knowledge argument to verify that the sender's NISC message is generated properly with respect to some private witness, which in this case is the input Y and the randomness the sender uses. This will also need to be simulated in the corrupted receiver case, which is why I'm bringing that up now. And this is in fact non-trivial because the simulator doesn't know the sender's input Y, only the result output by the ideal functionality. So in order to simulate both the NISC message and the zero knowledge argument independently of the sender's input, what we'll do is we'll add a second track to the functionality of both the NISC and the zero knowledge argument. So the receiver will now generate a random trapdoor T and commit to it alongside its input X, and it'll verify it within the internal NISC similarly to X. The sender now has the option to input the trapdoor into the NISC, as well as proving in zero knowledge that they did so rather than providing their input Y. And if they choose to do so, if they choose the second track and provide the correct trapdoor, they can input an additional value Z and program the output of the NISC by fixing it to Z. So what does this accomplish for us? Well, in the real execution of the protocol with an honest sender, this doesn't make a difference. The sender will just input Y into the NISC and a zero knowledge argument like they did before and complete the execution that way. But now in our idealized interaction with the simulator and a malicious receiver, the simulator can use the helper H to extract the trapdoor T from the receiver's message, use the trapdoor instead of Y, which they don't know, to complete the NISC and zero knowledge argument, and program the output of the NISC to whatever is returned from the ideal functionality to complete the interaction. That completes the case of a corrupted receiver. In fact, we're almost done with the corrupted sender case as well, since we already added a zero knowledge argument to verify the sender's message. There's one thing that remains, which is to provide a commitment to the sender's input Y so that we get the same extractability property as we added earlier for the receiver's input X. And to do this, we augment the zero knowledge argument by adding commitments to the respective witnesses for each track. And we additionally prove that those commitments are valid. This serves a double purpose. So first of all, like I was just discussing, this adds extractability for the sender's input Y in the corrupted sender case. And what's more, it adds an argument of knowledge property to the zero knowledge argument where the sender intuitively proves not only that their witness exists, but also that they know it. So what we get out of this is ensuring that the corrupted sender can't provide a valid witness to the second track of the functionality without having actually recovered the correct trapdoor T and broken the CCA security of the commitment scheme, since in this case, the trapdoor T was committed to by an honest party. So actually at this point, we now have the finished protocol, and to recap and illustrate, I'll briefly go over how we constructor simulators for the proof of security. So first, recall it as our simulator is restricted to helper-aided polynomial time. We'll have to avoid using the simulators for the underlying NISC and zero-knowledge argument because they specifically require super polynomial time. Instead, we need to rely on the decommitment helper H to provide the extractability property. So in the corrupted receiver case, the simulator will begin by receiving the first message from the adversary, and it will use this helper functionality to decommit the commitments to X and T and retrieve the input X and trapdoor T. And of course, recall that if those commitments aren't generated properly and consistently with the receiver's inputs, the internal NISC will just reject anyway. So next, it sends the extracted input X to the ideal functionality, which will return the result Z star of F applied to X and the honest sender's input Y. And then finally, it'll complete the interaction using the second track of the NISC and zero knowledge functionality by inputting the extracted trapdoor T and hard coding the NISC output to the result Z star that it got back from the ideal functionality. This ensures that the corrupted receiver receives a final message that opens to the correct output of the functionality, while also ensuring via security of the NISC and zero knowledge argument that the adversary can't distinguish this final message from a message in the real interaction that would use the first track. So in the corrupted sender case, the simulator doesn't know the true receiver's input X, and it begins by sending a simulated first message which commits to a dummy value, 0, instead of X, but is indistinguishable due to CCA security of our commitment scheme. It then receives a response from the adversary and aborts if the NISC or ZK reject. Since the adversary is unable to retrieve the trapdoor T without breaking CCA security of the commitment scheme, what that means is it's overwhelmingly likely that if it submitted an accepting zero knowledge argument, it must have used a valid witness and commitment to the first track, which by definition must include an input Y consistent with the sender's input. So in that case, the simulator will retrieve the commitment to the first track witness from the sender's message, use the helper to retrieve the sender's input Y from that, and in turn send it to the ideal functionality, which computes F and Y in the honest receiver's input X and returns the correct result to the honest receiver to conclude the protocol. So with my discussion of the protocol and simulators complete, to summarize, we present the first known round, minimal, or non-interactive two-party computation protocol, which satisfies a strengthened definition of concurrent and composable security. Specifically, it satisfies Oracle-aided or Angel-based UC security against malicious adversaries in the plain model. And it's constructed based on standalone SPS secure NISC and CCA secure non-interactive commitments. Furthermore, as an additional result, we show that these assumptions are not only sufficient, but also necessary to construct UC secure NISC. While the details of the second theorem were omitted from this talk due to time constraints, we do formally present and prove that theorem and its respective construction in the paper, along with the details and formal proof of our main results. And with that, I'll conclude. Thanks for attending, and I will take questions with what time we have left.
Thank you, Andrew. Do you have any questions from the audience here in the room? Okay, I don't think we have questions from the room here, and there's no question in the Zoom chat. I just had a quick question. You mentioned that you needed this non-interactive zero knowledge functionality, and it follows from the NISC protocol.
Yes.
Are you assuming that the underlying NISC is semi-honest security or
malicious?
I see. Okay, but in a standalone setting or?
Right, yes,
okay.
So the underlying NISC is standalone maliciously super polynomial time simulatable secure.
I see, but for the NISC, you only need it to be standalone secure, then you don't need the NISC to be concurrently secure.
Yeah, it's just standalone secure. So we can implement it using, we can implement it using the standalone secure NISC that we assume for the basis of our construction.
Okay, great, thanks. And any questions? Okay, I think there are no other questions. So let's thank the speaker.
Thank you.
So our next talk is attaining guaranteed output delivery beyond honest majority with friends and foes. And I think Protic Paul might be giving the talk, or there might be some special arrangements.
Hi, is it possible to play the recorded video? Hello? Thank you.
Presenting our work Attaining GOD Beyond Honest Majority with Friends and Foes. This is a joint work with Aditya Hegde, Nishad Koti, Varsha Bhatkukala, Arpita Patra, and Protik Paul. Let me begin by defining secure multiparty computation, also known as MPC. MPC allows n mutually distrusting parties, say P1 to Pn, each holding a private input to compute a joint function of their inputs. This distrust among parties is modeled as a centralized adversary, which can corrupt up to T out of the n parties. Now, any MPC protocol is required to satisfy the following properties: correctness of the output computed and privacy. That is, nothing beyond the function output should be revealed to the adversary. Now, although the classical definition of security for MPC does talk about what is revealed to the adversary, it does not take into account the leakage of information towards the honest parties. That is, an adversary can actually leak information towards honest parties by sending across its entire view to them, and this wouldn't be considered as a breach of privacy. In fact, several protocols in the literature actually leverage this loophole in the privacy definition in order to achieve the strongest security of guaranteed output delivery, or GOD, which allows the honest parties to receive their output irrespective of the adversary's strategy. The way these protocols achieve it is that they require all the parties to send their private inputs to a designated party which is identified to be honest, or a trusted party, TTP, which computes the function and returns back the output to these parties. Now, although this allows you to achieve GOD, in practical scenarios where the MPC protocol is deployed, these parties may be actually servers owned by different companies. In such a case, even though the servers are honest, leakage of information to each other may not be a feasible solution. This is where the notion of friends and foes security, or FAF security, defined in the work of Elon et al. Comes into the picture. Here, instead of modeling every party as purely honest, it tries to model them to be at least semi-honest. For this, in addition to considering a malicious adversary, which can corrupt up to T of the parties, it also considers an additional adversary, which can corrupt up to H star of the remaining parties in a semi-honest manner. To capture the view leakage from an adversary, it allows the malicious adversary to send its entire view to the semi-honest one. Now, the security is required to hold in the face of both these adversaries. That is, the private inputs of n-t parties not under the control of the malicious adversary are required to be secure. Additionally, the inputs of the n-t-h star parties not under the control of either of these adversaries are also required to be private. Given that this friends and foes notion is more practically relevant, in this work, we focus on constructing FAF secure protocols. Our contribution here is twofold. On the theoretical side, we prove the necessity of oblivious transfer, OT, for constructing a generic T, H star FAF secure protocol when n is lesser than or equal to 2T plus 2H star. This subsumes the optimal corruption threshold of achieving fair or GOD MPC in this model when n is lesser than 2T plus H star as defined in the work of Elon et al. Given this, we focus our attention to the small population MPC protocols and construct a protocol quad squad, which is a 4-party protocol which can tackle one malicious and one semi-honest corruption. Our protocol has two variants, fair as well as GOD. Note that in the 4-party setting, this is the optimal corruption threshold as defined in the work of Elon et al. To ensure efficiency, we operate in the pre-processing paradigm, which consists of two phases, an input-independent but a function-dependent pre-processing phase, where most of the computationally intensive tasks are carried on, and an online phase, which is input-dependent. Also, we construct our protocol over rings in order to leverage the CPU architecture. Finally, we show the applicability of our protocol in the domain of privacy-preserving machine learning, PPML, to show its practical relevance. Coming to our theoretical result, the necessity of OT, we prove this by reducing a T, H star FF protocol, say PyF, to a 2-party semi-honest OT protocol, PyOT. For the sake of this presentation, I'll assume n equal to 2t plus 2h star. However, in the paper, we show this reduction for all n lesser than or equal to 2t plus 2h star. So consider the protocol PyF for the following functionality. Party P1 has input as two messages, say M0 and M1, and party Pn has an input bit P. The remaining parties do not have any input to the functionality. The output of the functionality is as follows. All the parties excluding Pn receive a bot, whereas the party Pn receives message MB. Now, in order to reduce this protocol to an OT protocol consisting of a sender and a receiver, we do the following. The first T plus H star parties are emulated by the sender of the OT protocol, say PS, and the remaining T plus H star parties are emulated by the receiver PR. Note that the sender in the OT protocol has an input of two messages, which corresponds to the input of P1 in the protocol PyF. And similarly, a receiver in an OT protocol has an output message, say MB, and an input bit B, which corresponds to the input and output of the party Pn. Now we note that whenever a sender is corrupt, it corresponds to a corruption of T plus H star parties in the underlying FF secure protocol. And given that this corruption is semi-honest, since we consider a semi-honest OT protocol, the corruption in the corresponding protocol PyF is also semi-honest for these T plus H star parties. And this is exactly the idea that we use in order to prove the security of the OT protocol. Moving on to our practical results, before actually going into the construction of our protocol, I will go over the communication costs and its comparison with the existing works. So in the paper, we have compared our protocol quad squad to the state-of-the-art 4-party protocols in the honest majority as well as the dishonest majority setting. And here, we have reported the communication costs in terms of field or ring elements, depending on what is the underlying structure that the protocols use. And also the cost is reported per a multiplication gate. And we note here that our FAIR as well as GOD protocol have a comparable online cost to that of the state-of-the-art honest majority protocols of Tetrad and Fantastic 4. Although the pre-processing cost in our case is higher, this is justified by the necessity of OT, which we have already proven. And additionally, our protocol also tackles a stronger adversary compared to the honest majority. That is, it has one additional semi-honest corruption which it can handle. On the other hand, our protocol completely outperforms the dishonest majority protocol of Mascot, both in the pre-processing as well as the online phase, while improving the security guarantee from abort to FAIR and GOD. It is also important to note here that we achieve our GOD protocol with the same online cost as our FAIR protocol. Moving on to the approach that we take in our case. So we view the function as a circuit, which is evaluated in a topological order. Now at a very high level, this evaluation occurs in 3 phases: input sharing, the actual evaluation of the addition and multiplication gates, and output reconstruction. For the sake of this talk, I will be focusing on only the evaluation phase, wherein addition happens locally, so we'll be focusing more on the multiplication. For every subprotocol that we design for each of these phases, we follow the following idea, high-level idea. So either each subprotocol will complete successfully, or we identify, in case of a malicious behavior, we identify a dispute pair which is guaranteed to include the malicious party. So if we stop at this phase of dispute identification, then what we get is a fair variant of our protocol. And to improve the security guarantee to GOD, we run a semi-honest 2PC amongst the parties outside the dispute pair. Note that since the dispute pair already includes the corrupt party, a semi-honest 2PC protocol is sufficient. Finally, in order to maintain the same online cost from the fair to the GOD protocol, we use the segmented evaluation approach, wherein we break down the entire circuit into chunks of segments which are evaluated sequentially. Before going to the protocol construction itself, I'll briefly describe the challenges involved in moving from fair to GOD MPC. So consider two segments, SM-1, whose outputs are given as inputs to the segment SM. Now, in the case when we are running the 4PC protocol which we have designed, both these outputs and the inputs are in the 4PC sharing semantics. Now, consider the case when the segment SM-1 completes a successful evaluation and its outputs are in the 4PC sharing semantics. However, when we now come to segment SM, some malicious behavior is detected here and we end up identifying a dispute pair. This segment has to now be rerun with the 2PC amongst the parties outside the dispute pair. So what we have now is the segment SM-1 with its output in the 4PC sharing semantics. And we require the segment SM to be rerun with the inputs being in the 2PC sharing semantics. This requires a share conversion to be in between these two phases. Now, in the honest majority setting, such a share conversion can be done in a non-interactive manner due to the high redundancy involved in the sharing. However, in our case, since we are tackling a stronger adversary, our sharing semantics inherently have this higher threshold of sharing, which we will see in the following slides, due to which the redundancy is lower. This requires our share conversion to be actually interactive. So note that once we execute the segment SM with 2PC, all the following segments will be run only with 2PC. So the only rerun that we have done here is for this particular segment SM, which allows us to retain the cost from fair to GOD protocol. Let me begin describing our protocol pod spot, starting with the sharing semantics. To ensure efficiency by operating over rings, we rely on replicated secret sharing, also known as RSS. Here, in order to tackle the corruption of one malicious and one semi-honest, with the view leakage which is possible, we consider a threshold of corruption of 2, which leads us to 4,2 RSS sharing. This implies that a secret is divided into 6 components in such a way that every pair of parties holds a common component. Say party P1 and P2, for example, hold the component S12. In contrast to the honest and dishonest majority setting, we have a higher number of share components, which poses a challenge in ensuring efficiency in our protocol. Instead of considering a replicated secret sharing of a value directly as described, we tweak the sharing slightly in order to achieve a better efficiency in the preprocessing paradigm. And for this, to share a value, we consider 2 components of sharing. One is a mask, say alpha x, which is replicated secret shared as described before. In addition, we consider a masked value, which forms the second component of the sharing, say beta x, which is equal to the actual value x plus the mask alpha x. Now, this can actually be viewed as RSS sharing of the value x itself as follows. The way this helps us is that the first component of the sharing, alpha x, can be computed during the preprocessing phase, whereas the second component, beta x, can be made available during the online phase. As mentioned, I won't be describing the input sharing in the output reconstruction phase. Instead, I'll directly go to the multiplication protocol in our case. So consider a multiplication gate with inputs x and y and output z. Now, the goal of a multiplication protocol is the following. Given the sharing of the input wires x and y, which consists of the two components I described before, the goal is to compute the sharing of the output wire, say z. Now, using known techniques in the literature, it is already known that this can be reduced to a reconstruction of one element, which is beta z in our case, in the online phase, and a computation of the multiplication triple, which corresponds to alpha x, alpha y, and alpha x times alpha y in our case, in the pre-processing phase. So this is exactly what we do in our protocol, and I'll detail these reconstruction and the triple generation in the subsequent slides. Coming to the reconstruction protocol, we see that in the sharing of any value, say z for example, any party misses three components of the sharing of the mask, that is alpha z in this case. For example, consider party P1, it misses the shares alpha z23, alpha z24, and alpha z34. Now, each of these components is actually held by two other parties. For example, alpha z23 is held by party P2 and P3. However, requiring the parties to simply send across this value to P1 does not suffice. Consider the case when one of these parties is malicious. It can send an incorrect value to P1 and P1 wouldn't be able to identify the correct value out of these two. For this, we use a primitive called as the joint message passing or jump primitive defined in the work of Coty et al. This primitive allows two parties holding a common message to send the message to one or two other parties in such a way that either the send is successful and the parties receive the common message, or a dispute pair is identified. So the way we approach our reconstruction is as following. Every pair of parties holding the component which is missing for party P1 sends it across to P1 using the joint message passing or jump primitive. Now the communication cost in this case for a jump primitive is one element if you're trying to reconstruct to a single party. So a reconstruction towards one party in the following manner would require 3 elements of communication, which corresponds to 12 elements of communication when you're trying to reconstruct the beta z towards every party. So given this, we reduce our communication cost for multiplication, which in turn requires this reconstruction, from 12 elements to 7 elements using some optimization, which requires 3 rounds in total. Moving on to the multiplication triple generation. Note here that we are trying to compute the sharing of alpha x times alpha y, given the sharing of alpha x and alpha y. We note that writing alpha x alpha y in terms of the shares of alpha x and alpha y results in 36 summons. We categorize these 36 summons into 3 types based on the number of parties which can compute them locally. For example, we have summons of type S2, which can be computed by 2 parties locally, summons of type S1, which can be computed by a single party locally, and summons of type S0, which cannot be computed by any party locally. For summons of type S0, we use OTs in order to perform this computation. For summons of type S2, two parties compute these values locally and complete the sharing. For summons of type S1, we note that 6 summons each can be computed by one party. So we make this party compute the sharing of these summons and finally give a zero knowledge proof that they have indeed done this computation in a correct manner. So this summarizes the 2 components of our multiplication. Summarizing the cost of our protocol again, we see that the online communication of 7 elements actually corresponds to the 7 element reconstruction, which I just described, which happens in 3 rounds. And the retaining the cost from FAIR to GOD protocol for the online case comes from the segmented evaluation approach. Finally, coming to the PPML benchmarks, We have benchmarked the neural network inference task over the MNIST dataset by instantiating servers across different continents using Google Cloud Platform. Now we note that although the total communication cost of a protocol, the fare as well as the GOD variant is comparatively higher than that of the honest majority protocols, the online communication cost is indeed comparable. Given that our protocol tackles a stronger adversarial model, which is practically relevant, it becomes a very much feasible option to be used in practice. The code for our protocol is available publicly at the link provided. Thank you.
Hello everyone, my name is Shashali. I'm going to introduce our paper in Asiacrypt 2000.
Do we have any questions for the audience? We usually say to thank the speaker, but it's a pre-recorded talk, and I think the speaker is not in the Zoom rooms. But any questions for one of the co-authors for the paper? All right, I guess we should thank them for the pre-recorded talk. Maybe we can move on to our next speaker then. Okay, all right, so our final talk for the session is towards practical topology hiding computation by Shashwai Li.
Hello everyone. Can you hear my PPT? Can you see my PPT? Hello everyone. Can you hear me?
Yes, we can hear you.
Okay. I'm sorry. Okay. Can you see my PPT? Okay, hello everyone. My name is Shashai Li. I'm going to introduce our paper in Asiacrypt 2022. The title of our paper is Towards Practical Topology Hiding Computation. Secure multiparty computation allows n parties to securely compute some function without leaking additional information about the inputs. Classical MPC assumes that either two parties can communicate directly. Namely, the communication graph is complete. So what if the communication graph is incomplete and even sensitive? Moran, Odlov, and Richardson formalized the concept of topology hiding computation. Informally speaking, a TCP protocol is an MPC protocol over incomplete graph, which doesn't leak any information about the communication graph. In the setting that an adversary may statically, passively corrupt any number of parties, TCP has been shown to be feasible on any graph. Akavir, Lovini, and Moran showed that TCP is feasible over general graphs. This implies that any function can be topology hidingly computed over any graph. The reason is that if there exists a topology hiding broadcast for some graph class and a PKE scheme, then TCP exists for the same graph class. We know that MPC computing any function exists. To construct a TCP protocol for computing some function f, we just use TCP and PKE to simulate point-to-point channels in an MPC protocol computing f. Assume that Pi wants to send X to PG. They do the following. Firstly, PG uses TCP to broadcast its public key. Then, PI encrypts the message X using the public key of PG, and then uses THB to broadcast the resulting ciphertext. Finally, PG can decrypt the received ciphertext to get X. Other parties know nothing about X because they do not know the decryption key. A key true in existing THC protocols is PKCR encryption. This is a special PKE scheme. With PKCR, one can add or delete a public key layer to or from a ciphertext. Namely, with PK and an encryption of X and key, one can generate an encryption of X and key times PK, and an encryption of X and K times the inverse of PK. In some of our protocols, we require the PKCR to be linearly homomorphic. We refer to the paper for more details. Although THC has been shown to be feasible, existing THC protocols are not practical. In this paper, our goal is to improve the efficiency of several existing THC protocols on circles and general graphs. Firstly, we consider the broadcast functionality. The AM and ALM protocols are the state-of-the-art THB protocols on circles and general graphs respectively. They are designed for broadcasting a single bit and built by first presenting a topology heading OR protocol, and then letting the broadcaster take the broadcast bit as input, and each other party take 0 as input. The AM and ALM protocols can be described in the same framework. This framework contains two phases, the aggregate phase and the decrypt phase. The aggregate phase takes T rounds, T equals n-1 in AM, and 8 times the third power of n times kappa in ALM. At the first round, for each party PI and each of its neighbor D, PI encrypts its input bit to C and a fresh public key PK, and sends PK and C to its neighbor D. At each following round, each party PI chooses a permutation sigma of the set of its neighbors. AM uses the only non-identity permutation, and ALM uses a fresh random permutation. Then, for each ciphertext received from neighbor D, PI adds a public key layer and homomorphically adds its input bit to this ciphertext, and then sends the resulting ciphertext to neighbor sigma D. The decrypt phase also takes T rounds at the end of the aggregate phase. Each received ciphertext has been the OR of all the inputs. To decrypt these ciphertexts, the parties send each ciphertext back through the same work is traversed during the aggregate phase, and each party deletes its own public key layer in the reversed work. Now, we saw how to improve the AM and ALM protocols. Akavia, Levine, and Moran observed that computing an encryption of A or B from A and an encryption of B does not require any homomorphic property of PKCR. If A equals 1, then the computing party outputs an encryption of 1. Otherwise, it outputs an encryption of B. Our observation is that computing OR is okay for broadcast. If we only consider broadcast, then we let the parties do the following. If the computing party is the broadcaster, output an encryption of A. Otherwise, output an encryption of B. In this way, the broadcast value does not need to be a bit. Namely, any plain text can be broadcast. In the original AM and ALM protocols, each party needs to send a ciphertext to each neighbor and each round for broadcasting just a single bit. Note that a ciphertext is of length at least all kappa bits. With optimization, if we instantiate PKCR with egomorph scheme, then we can set the plain text length to kappa bits and the ciphertext length to 2 times kappa bits. Namely, kappa bits can be broadcast with each party sending a ciphertext of length of kappa bits to each neighbor at each round. Therefore, the communication costs for both the AM and ALM protocols for broadcasting kappa bits are reduced by a factor of O kappa. Now we consider the sum functionality. The only topology hiding sum protocol on circles is compiled from the AM protocol. Using additively homomorphic inclusion, a secure sum protocol can be constructed as follows. Firstly, each party encrypts its input and sends the resulting ciphertext to P1. Then, P1 homomorphically adds all the ciphertexts. Finally, the parties distributedly decrypt the final ciphertext. As we stated in our paper, this protocol has linear communication cost, O(n) times kappa bits. Recall that topology hidingly sending a single bit using the AM protocol will cost O(n) squared times kappa bits. By compiling this sum protocol into a THC protocol, we obtain a topology hiding sum protocol with the communication cost O the third power of n times kappa squared bits. Our idea is that instead of compiling black box from THB, we modify the AM protocol to be a topology hiding sum protocol. To achieve this, we require the parties to know the value of n and the PKCR to be additively homomorphic. Note that the AM protocol only assumes that the parties know an upper bound of n, and so does the THS protocol compared from the AM protocol. In the AM protocol, each party homomorphically adds its input bit to each received ciphertext. Instead, we let each party homomorphically add its input value to each received ciphertext. The efficiency of this THS protocol has the same asymptotic communication cost as the AM protocol, namely O(n) squared times kappa bits. Now, let us consider the general computation functionality. As before, the only general topology hiding computation protocol on circles is compiled from the AM protocol. We consider a general computation protocol based on additively secret sharing, which contains three phases. In the input sharing phase, each party additively shares its input, which requires to send O(n) shares. The total communication cost of the input sharing phase is O(n) squared times kappa bits. In the circuit evaluation phase, the parties compute the circuit gate by gate. Addition gates can be computed locally. The parties can compute a multiplication gate using linearly homomorphic encryption, resulting in O(n) times kappa bits communication. The total communication cost of the circuit evaluation phase is O(c) times n times kappa bits. In the output recovery phase, each party sends its share to P1, and then P1 computes the sum of all the shares. The total communication cost of the output recovery phase is O(n) times kappa bits. By compiling this MPC protocol into a THC protocol, we obtain a general topology hiding computation protocol with communication cost O the first power of n times kappa squared plus c times the third power of n times kappa squared bits. Now we saw how to share the inputs and recover the output more efficiently using our THS protocol. To share an input x, the input owner Pi samples a random value r, and each other party Pj samples a random share xj. Then the parties execute our THS protocol, where Pi takes plus r as input, and each other party Pj takes minus xj as input. All parties will get the output, which equals x plus r minus the sum of all other shares. Finally, Pi takes z minus r as its share. The total communication cost of sharing n inputs will be the third power of n times kappa bits. To recover the output, the parties execute our THS protocol, where each party takes its share as input. The communication cost of recovering the output will be O(n) squared times kappa bits. Now, we consider the circuit evaluation phase. The key point of circuit evaluation is to realize the multiplication functionality, which receives additive sharings of x and y, and returns an additive sharing of x times y. Our starting point is that a sharing of x times y can be computed as follows. Firstly, the parties generate a sharing of a random value R. Then the parties execute a protocol to let all parties securely get the value x times y minus R. Finally, the parties can locally compute a sharing of x times y. Note that a sharing of a random value R can be generated locally by letting each party sample a random value Ri and setting R to be the sum of all the Ris. The left goal is to publish the value x times y minus R. To achieve this, we require the parties to know the value n and the PKCR to be linearly homomorphic. To publish the value x times y minus R, we divide the aggregate phase into two subphases where each takes n-1 rounds. In the first subphase, each party homomorphically adds its share of x to each received ciphertext. At the end of the first subphase, the parties have encryptions of x. In the second subphase, each party PI first computes an encryption of x times yi minus ri, and then homomorphically adds this ciphertext to the received ciphertext. At the end of the second subphase, each party has the encryptions of x times y minus r. Finally, the parties execute the decrypt phase as in the AM protocol. The efficiency of our topology hiding multiplication protocol is O n squared times kappa bits. Our final result is an optimization for the LZM3T protocol of Lavini et al. This protocol is an FHE-based general topology hiding computation protocol on general graphs. In the aggregate phase of this protocol, each party PI appends the ciphertext of its input xi and its ID IDI to each received ciphertext. At the end of the aggregate phase, each party PI will receive T pairs of ciphertexts. The corresponding plain texts can be parsed as encryptions of all the inputs, and the parties can homomorphically compute the given function. In the aggregate phase of the LZM3T protocol, each party sends a ciphertext vector of length OT to each neighbor at the Tth round. Note that the total number of rounds is O the third power of n times kappa. Hence, the number of the ciphertexts sent by the party is O the 8th power of n times kappa squared during the aggregate phase. We give an optimization for the aggregate phase to reduce the communication. Our idea is that in the aggregate phase, each party sends ciphertext vectors of length n at each round, and for the ith entry of the ciphertext vectors, the parties act exactly as in our optimized ALM protocol, with PI being the broadcaster and the input of PI being the broadcast value. This way, at the end of the aggregate phase, the last party in each work will get a ciphertext vector containing the encryptions of all the inputs. Our optimized aggregate phase only requires the parties to send O the 6th power of n times kappa ciphertexts. This is a presentation of our paper. Thank you for listening.
Yeah, audience in the room.
What?
Oh yeah. Sorry, I heard a voice. Questions? Oh, sorry. Sorry. Actually, if there are no questions here, let's just take all the questions online and let's thank all the speakers in the session.